This is our entry for the American Concrete Institution EcoConcrete Student Competition 2021. From the University of Georgia, our team consists of Hannah Byram, Horst Chin, Dylan Glass, Tess Mosley, Brian Mungai, and Derek Scott.
Okay, going into our decision-making process and the materials chosen, the absolute volume method was used to determine the basic quantities of the cement designs. This method is based on the saturated surface dry condition, SSD. All table references are in reference to the Portland Cement Association Manual 16th edition and the Florida Department of Transportation Standard Specifications for Road and Bridge Construction, Section 346. Okay, so for the decision-making process and materials chosen, we have two different scenario mixture designs. Our first one is the base case scenario, and we have all the design requirements that were needed to satisfy the standards. We also detailed the FDOT requirement for pavement as well. We used the compressive strength of about 3,800 psi, and after doing all the calculations for water, cement, coarse and fine aggregate, and air, the quantities were calculated. For water, we have a weight of 175, cement 438, coarse aggregate 1,074, fine aggregate 600, and the air content percentage is 4.5%. Our other case scenario mixture design was our alternative case, and this was designed to be our more eco-friendly concrete mixture. The alternative case mixture was made to be more eco-friendly by using SCMs, or supplementary cementing materials. Specifically, we used fly ash, which decreases the amount of cement material used while increasing the long-term strength. As you can see by looking at our quantities calculated for the alternative case scenario, our cement weight has decreased significantly from our base case scenario. This is because we added fly ash, which now decreases the cement usage and also increases our long-term strength by using SCMs. All of the material for the base case scenario and the alternative case scenario mixtures will be coming from 3 different providers. This is detailed in Table 2.0 of provider descriptions.
The life cycle assessment is a method used to evaluate the inputs, outputs, and potential environmental impacts of the concrete mixture throughout its life cycle. For the mixture design, the EcoConcrete calculation tool version 2.01 was used. The formulas used in the life cycle assessment are to the bottom left of the slide. The image on the right describes the findings of the life cycle assessment, which I will discuss now. The environmental impacts concerned with the EcoConcrete design include global warming, carcinogenic, ozone depleting, ecotoxicity, and fossil fuel depletion factors. The factors were reduced by 30, 5, 30, 10, and 30% respectively. The requirement was to improve by 15% or more. Our design improved by an average of 21.5%. It is important to analyze the life cycle assessment because the system boundaries greatly affect its result. It starts off with pre-production processes, which include manufacturing and extracting raw materials. It ends with the transportation to the batching plants. The production and transportation processes affect the environmental score the most. The further the materials are away, the more energy it takes to produce the concrete. The Life 365 simulation determined that the service life for the base case scenario is 11.9 years, whereas the service life for the alternative case scenario is 23.7 years. The durability performance score is 1, and the lifespan increased by 11.8 years.